Do you know secondary beams are designed as restrained beams in steel buildings? In this tutorial, I will solve a practical example on restrained beam as per Eurocode 3. This is part 12 of lecture series on steel design. For other parts, please have a look at description down below. Hey friends, if you're new here, I am Dr. Jawed Qureshi, a senior lecturer at a London university. On this channel, we explore technical and human skills to help us lead more productive, happy, and examined life. In this tutorial, I will cover two practical examples. After you solve these examples by covering a step-by-step process, you will be able to confidently design a restrained steel beam. These two examples include steel beam with distributed and point loads and steel beam with distributed load only. Let us solve first example with distributed and point loads. In this example, the beam shown in figure 1 is fully restrained along its length and has a stiff bearing of 50 mm at the supports and 75 mm under point load. S275 steel for following loading. We have permanent actions on this beam. We have uniformly distributed load 15 kN per meter and we have a point load 3 kN. We have a variable action Q1 30 kN per meter and we have point load 50 kN. Now here you can ask me a question that, okay, Dr. Qureshi, you said on secondary beams we will just have UDLs, but here you have a point load. How come it is a restrained beam? If you're asking me this question, then I'm going to reply. If you're not asking me, then I'll just go ahead with the example.
Could you reply, please?
Oh, could you reply? Okay, excellent. So the answer to that is this beam is taking loading from slab because spanning direction is vertical one. And that will be distributed on here as UDL. And it is taking a point load from here as well. So if I draw its diagram is going to be like this. This will have UDL and this will have a point load as well, which is coming from the secondary beam. This is primary beam for these two spans and this is a secondary beam for these two. So how would you design it? I would design it as a restrained beam because it is taking UDL and there's a positive connection. So positive connection is not letting it move anywhere. So this is the situation where you will use this kind of beam. But normally you would have only uniformly distributed load in most of the situations. Yes, you just have to work out loading. You just have to classify the section. You just have to carry out these three checks. As simple as that. How do we work out loading? Gamma G is a factor, gamma Q is a factor, and we're using equation 6.10b where you have this C factor 0.925. So applying this formula for UDL, it comes out to be 0.925 is a factor. I'm using 6.10b, but you could be better off using only 6.10 where we don't apply this factor. That will still be fine. 1.35 times 15 plus 1.5 times 30. G1 and Q1 are given and the value that you get here is 63.7 kilonewton per meter. Point load, you will again apply the same formula, 0.925 factor for permanent load and 1.35 is gamma G into 40. Or you could simply say that 1.35 times 40 plus 1.5 times 50. That's still fine. But using 6.10b will result in greater economy. Not greater economy, some economy to be honest. Now I have the loading. This is a combination of UDL and a point load. A central point load, which means that my applied moment is going to be combination of WL square over 8 plus PL over 4. FED is applied load here, UDL, and FED2 is applied point load. Can I say that it will be WL square over 8 and PL over 4? Instead of W, we have used FED. FED means applied design load. What we have done is combination of moments for point load and UDL. This is giving us combined moment of 540 kilonewton. Now maximum shear force is going to be WL over 2. Now instead of WL, you can see that I'm applying FED. W is called FED and then you times it by L divided by 2 to work out total load. For the second one, because it's a point load, so you don't need to multiply with L to work out the total load. So in total, it comes out to be 270 kilonewton. This is applied shear and MED is applied moment. The formula for moment MCRD was WPL into Fy over gamma M naught. Gamma M naught is 1. For the time being, I'm assuming that the capacity of the section is equal to applied so that I can find out the section. This will make it MED is equal to WPL, sorry, not PT, PL into Fy. So from here, it will give me WPL as MED over Fy. And this is the formula which is being used here. For the time being, I do not know what is the class of my section, and I just have loading. I want to find out the section. And from here, I can find out this WPL, which is MED over Fy. Now, MED is my applied one, and I am converting it into centimeter cube. This is kilonewton per meter. I will convert this into Newton into millimeter, and then I will convert it back into centimeter cube. I have to divide this by 10 raised 3. So that's why 10 raised 3 is there. Why am I converting it into centimeter cube? Because I want to use section table. In section table, the unit for plastic modulus is in centimeter cube, 1964 centimeter cube. Now, once I have this value, I will go to Steel for Life blue book. Here, the thing which I want to observe is plastic section modulus. So I need 1964, above 1964. So I could use this section probably. I could use this section as well. 610 into 178 into 82. I could probably use this one, 533 into 90. I have so much of choice. Remember that use major axis plastic modulus, means the section is being loaded in its major axis. Now the chosen section is 533 which has WPL 2360. Its properties are here. Once we have these properties, then we can carry out other checks. We need to classify the section. The purpose for classification is that we want to use appropriate moment equation. Epsilon 235 over Fy, epsilon comes from the formula. Fy is material strength. This comes out to be 0.92. Flanges for CF, this is the formula for CF. B minus TW minus 2R divided by 2. B we have found out here, 209 minus TF is 15.6 minus 2 times R is 12.7 divided by 2 we get this CF, and CF over TF is 5.57, which is less than 9 epsilon. 9 epsilon is the limit for class 1. If you could go back here, you could see that this section has got CF over TF 5.57, which is directly given here as well. Now here you would say that, okay, Dr. Qureshi, why are you giving us a lot of trouble in finding this out? The reason is that you may not have all the section and section tables. So you may be working in different countries. You may be working with old sections. So it is important to find out these yourself. So the flanges are class 1 and internal compression part or web under pure bending. CW is given as D in section table. So D is 476.5 divided by TW from section table. And the limit for class 1 is 72 epsilon. And we multiply this epsilon that we worked out here. The web is class 1. Overall classification is class 1 for the section. And it means that I can apply this WPL Fy over gamma m naught formula. If it was class 3, then my assumption of using WPL would have been wrong. Then I would have chosen elastic modulus. But most of the sections in section table are class 1 or class 2 for beams. Once I have classified the section, I have to carry out 3 checks: moment, shear, and deflection. So MED over MCRD should be less than or equal to 1. MED is applied, and MCRD for class 1 sections is WPL. Recall from section classification that class 1-2 section plastic moment could be reached, and for class 3 sections it was in between plastic and elastic, so that's why we used elastic properties for class 3. And for class 4 we used effective sections. You will use WPL for the section, not for the one which was required. Our required was 1964 centimeter cube. Our chosen one had WPL 2360. Convert this centimeter cube into millimeter cube, then multiply it with 275. Units will be millimeter cube times Newton per millimeter square. This will give me Newton into millimeter. If I wanted to convert Newton into millimeter from small to large, I will divide it by 1000, then again I will divide it by 1000, which means that 10 raised minus 6. And that's the reason we've used this 10 raised minus 6. Remember to have consistent units. This will give me 649 kilonewton meter as moment capacity. Now 540 is applied, 649 is capacity, it's 0.83. So section is fine in moment. If this value was greater than 1, what would you do?
Choose a different section.
Choose a different section. Excellent. With higher WPL. The next thing for me to check is here. So VED over VCRD. VED is applied, which we found out little earlier. VPLRD is AV FY under root 3. FY is material strength. For our section, the area is 533,210.92. Area is 117 centimeter square. You have to convert this centimeter square into millimeter square because B, TF, TW, TR, all these things are in millimeter. If you don't convert this into millimeter, then you will get answer in negative, which is wrong. So don't make this mistake. Always convert it into millimeter. From here, B, TF, TW plus 2R, I got all these values from section table. I showed you where are these values. When you put these values, you get 5724 millimeter square. The value should not be less than nu HWTW. We put value of nu, put value of HW, put value of TW. So HW is overall height minus 2 times thickness of flange. AV comes out to be 5724. If this is less than 5069, then standard value, then use this value. Once we have got AV, we will put it back in this equation. Because it will result in newtons, to convert it into kilonewtons, we have multiplied it with 10 raised minus 3. The reason is that this is AV is in millimeter square, material strength is Newton per millimeter square. This and this will get cancelled. You will be left with newtons. So to convert newtons into bigger unit, kilonewtons, you have to divide it by 1000. Demand versus capacity is 0.3. Now remember that this is less than 0.5. If it was more than 0.5, we will consider combined effect of bending and shear, and that will reduce the moment. But this will not be the case for most sections in section table for building use. And then finally, we have to check the deflection. Convert everything into millimeters. Now Q is in kilonewton per meter. So even if I convert it into millimeters, it will still be the same value. So if it is 5, if this is 30, if I convert kilonewton into 1000 and meter into millimeter, this and this will get cancelled. So this will still have the same units. So I don't have to do anything to 30 because Newton per millimeter will be the same. So that's the reason we have 30 here. Now remember that this 30 is unfactored variable UDL load. Length is 6.5 meter, converting it into millimeters over 384 plus P is 50 kilonewton, that is the point load, and this is unfactored point load, times by length cube 6.5 meter, converting it into millimeters, divided by 48, and I is the second moment of area. You get it from section table, but you get it from section table in centimeter power 4. You have to convert it into millimeter power 4, and then E for steel can be taken as 210 gigapascal, or I can say that 210,000 Newton per millimeter square. Once you put all these values, you get W, or you can call it as deflection as well, or small w. Then you have to compare it with the limiting value. The limiting value is span over 360. Span is 6.5 meter divided by 360, it will give me 18 meter. Certainly this is less than 18 millimeter, which means that serviceability is fine. Now serviceability is a major issue in restrained beams. When it does not satisfy serviceability, you choose a next deeper section. When the depth is more, it will increase I, second moment of area, and as a result it will reduce the deflection.
The second example is related to steel beam with distributed load. Let us solve this example. In second example, I'm going to solve a real-life restrained beam located in a building, and this example is taken from P387 Steel Construction Institute Guide Steel Building Design Worked Example for Students. This is the plan of the building. We have to design this beam G12. The elevation typical section of the building is given and a braced bay is over here. You can see that beam G12, it is taking load from slab on the top and bottom. So beam is taking load from both sides. This is termed as bay width, which is 3 meters each side. In total, it is 6 meters. If I was designing a beam which is edge beam, bay width will get reduced to only 3 meters. But here, this beam is taking loading from two sides of the slab. The permanent action includes self-weight of the floor, which is 3.5 kilonewton per meter square, and self-weight of the services. In total, the permanent action or small gk is 3.7 kilonewton per meter square. Variable action, because this is the office building, category 1 from Eurocode, it is 2.5 kilonewton per meter square. We have partitions, which is 0.8 kilonewton per meter square. In total, variable action or GK is 3.3 kilonewton per meter square. Let us see how we can solve this problem. So we have simply supported beam. The length of the beam is 8 meters, which is from here. So you can see that length is 8 meters. Bay width for this intermediate beam is 6 meters. The permanent action is 3.7. Variable action is 3.3. First thing, we have to work out the design load. The partial safety factor for permanent action is 1.35. Partial safety factor for variable action is 1.5. The reduction factor C is 0.925. I'm going to use equation 6.10b. So the design value of combined actions is C gamma G GK plus gamma Q QK. Putting all these values here, gamma G and gamma Q we just determined. Putting all these factors, we get 9.7 kilonewton per meter square. This is the design load, but it is distributed on floor. Now, UDL per length of the beam, accounting for bay width 6 meter, it will come out to be 57.4 kilonewton per meter square. So if I draw its diagram, it will look somewhat like this. So it has a UDL of 57.4 kilonewton per meter, and the length of the beam is 8 meters. So firstly, we have to work out the design moment and shear. The design moment is WL square over 8. So we put W, we get it from here. Here we call it as FT or design load. L is 8. We get 457 kilonewton meter. Then we will work out design shear force, which is WL over 2. Here W is called as FT, and this comes out to be 230 kilonewton. Now these loads are applied loads. We have to work out the design capacity. In restrained beams, we check 3 things: moment resistance, shear resistance, and serviceability or deflection. Deflection is one of the key criteria in restrained beams. Secondary beams are designed as restrained beams. If the beam passes serviceability check, almost certainly it will pass moment check and shear check. Usually, shear is not a big issue in restrained beams and can be neglected in calculations for building use. But if a beam is carrying heavy concentrated point loads, if it is a plate girder, if it is used in bridges, then you have to take into account shear. But here I will follow the process. I will carry out all 3 design checks: moment, shear, and deflection or serviceability. Firstly, we have to come up with a trial section. Assuming S275 is steel, then I will go to table 3.1 and find out its yield strength. S275 is steel. I'm assuming thickness is going to be less than 40 millimeter. For off-the-shelf sections available in section table, most of them, they have thickness of flange or web less than 40 millimeter. Then you can see that for S275 steel, the Fy is 275. First, we have to come up with trial section. And here we will assume that our applied moment is equal to the moment capacity of the section. In this way, we will work out WPLY MYD into gamma M naught over Fy. This formula actually comes from MCRD equal to WPLEL into Fy over gamma M naught. We assume that MCRD is equal to MED. And from here, we get 1669 centimeter cube. Now we have to go to section table to see which section has WPL greater than 16699. Now here you have to choose plastic section modulus in YY direction. The beam is loaded on its major axis direction. So this is 1830, which is greater than our required section modulus 1669. So we choose this trial section 457.191.82 S275 steel with provided WPL as 1830. Now, these are all the section properties that we have got from section table or Tata Steel Interactive Blue Book. Simply type in steel for life in Google, it will come up as this. Modulus of elasticity for most of steel is 210 gigapascal. So firstly, we have to classify the section. So epsilon is 235 over Fy. Fy is 275. We get value of epsilon as 0.92. First, we have to work out outstand flanges. So Cf is equal to B minus Tw minus 2R over 2. B is the width. Tw is thickness of web. R is root radius. When we put all these values, we get value of Cf as 80.5. And Cf over Tf comes out to be 5.03. Now we have to compare this value with the limiting value in table 5.2. In table 5.2, outstand flanges, the limit for class 1 CF over TF is 9 epsilon. CF over TF is less than 9 epsilon. 9 epsilon comes out to be 8.28. So this value is less than 9 epsilon. This means that the outstand flanges are class 1. Then I will move to CW over TW. CW is equal to simply D, which is depth between fillet, which is 407.6 from section table. This comes out to be 41.17. I have to compare this value with internal compression part. Here I'm classifying a beam, which means web will be subjected to bending, not compression. If I was classifying a column, then I will use this part subjected to compression. But here I'm using a beam. CW over TW 41.17, that is less than 72 epsilon. We put value of epsilon. It means that the web in pure bending is class 1 as well. This means overall classification under pure bending is class 1 for this section. If you like, for this section, CF over TF and CW over TW, they can be directly obtained from a section table as well. Now I have to carry out the member design checks. So let us first of all check the shear resistance. Shear normally is minimal in these beams. So VED over VCRD should be less than or equal to 1. VCRD is VPLRD AVFY over under root 3 divided by gamma m naught for class 1 sections. For rolled sections, remember web is going to take shear mostly. The formula for shear area is A minus 2 BTF plus TW plus 2R into TF, but this should be less than or equal to nu HWTW. If we put all these values here, we get shear area of the section. Value of nu is 1. Nu HW over TW. HW is height of web and TW is thickness of web. We get this area as 4237 millimeter square. As our AB is greater than nu HWTW, so AB will be equal to 4763. If it is not, then you will adopt this value. The design shear resistance, if you put all these values, we get shear resistance as 457, and applied versus the capacity comes out to be 0.3 as expected. So section is fine in shear. Effect of combined action of moment and shear should not be considered because this value is less than 0.5. If it is more than 0.5, then shear is going to reduce the moment, and there are formula which you can have a look at earlier lecture in part 11. Shear buckling happens when web is unstiffened and where heavy concentrated point loads are applied. Most of the time it's not a big issue in buildings, but we will check it here. The HW over TW should be less than 72 epsilon over nu. If we put all these values, you can see that this condition is satisfied. When this is satisfied, it means that effect of shear buckling should not be considered. If it is not satisfied, then you should consider having stiffeners in the web. When you put stiffeners in the web, then it will prevent shear buckling. And shear buckling mostly happens if you have heavy concentrated point loads on beams. Then we have to check moment resistance, MED over MCRD. This will certainly pass because our WPL was more than required WPL. So MCRD is WPL Fy over gamma m naught for class 1 sections. If you put all these values, the moment capacity comes out to be 503 kilonewton meter. The applied moment is 459 and the capacity is 503, comes out to be 0.91, which means that the bending resistance is fine. The next and most important thing is serviceability check. This is the secondary beam. For secondary beam, serviceability check is absolutely critical. If this beam passes serviceability check, it means that it will almost certainly pass all other checks. So let us check vertical deflection. So vertical deflection should be considered only for unfactored variable loads. Permanent actions should not be included, and this is according to Annexure 2.23. QK was 3.3 kilonewton per meter square. If we multiply it with bay width, we get 19.8 kilonewton per meter. So 5L length is 8 meter. We convert it into millimeter. Everything has to be converted into millimeters. IY from section table, IY has to be major axis IY. When we put all these values, we get this deflection as 13.6. And this has to be less than the deflection limit. Deflection limit, the most common one is span over 360. This is 22.2. The deflection is less than deflection limit. It means that the beam is fine for deflection. If it is not okay in deflection, then you will choose a deeper section. We can now say that 457, 191, 82, UKB section in S275 steel is fine for this beam. In this way, you know how to design beams now, at least restrained beams. In our next lecture, we will talk about unrestrained beams, which is the case for most primary beams. I hope you enjoyed this lecture, and I'll be happy to take any questions. So please comment below and then you will get the answers. And I will see you in my next lecture on unrestrained beams. All design formula discussed in here are in this website bit.ly/steel design. If you go to this website and no sign in is required, if you click on part 11 and 12 restrained beam, it will take you to this 2-page design recipe where all design checks are mentioned for steel beam.